Okay. Hello there. Are you okay? Today, let's discuss again advanced mathematics, and the topic today will be algebra, and the subtopic will be mathematical induction, as it is presented to you today by Kimati John, a teacher from Jangwani Secondary School. And we shall discuss some few rules, and we shall also see some few examples on how we can find or we can prove the propositions that require the principle of mathematical induction to prove. Some of the students do find some problems in proving some propositions. Now let's use a very simple propositions to remind ourselves on how we can use these principles of mathematical induction to prove some propositions in mathematics. Now, in mathematical induction, we shall use, what we are doing now, we shall cover the following. We shall cover the mathematical induction, the principle. I will state the principle, or just try to explain the principle, and the steps used to prove some propositions by using mathematical induction or the principle of mathematical induction. And then we shall see some few examples on how we can prove those propositions by using the steps that we discuss. I will discuss later on, and then I will leave some few questions for you to practice more. Now let's start. The principle of mathematical induction. The principle of mathematical induction. Now the principle of mathematical induction, as it is seen there, it says if the basis steps and the inductive steps are proven or proved to be true, then the statement is true for all natural numbers. I'll repeat. The principle of mathematical induction states that if the basis steps and the inductive steps are proven or proved to be true, then the statement is true for all natural numbers. Then the statement is true for all natural numbers. Now let's see, what are those steps and how can we prove those propositions? Now let's see some few steps, and then we shall go to some few examples, my dear student. Now the steps that we'll be using in proving these will be as follows. First of all, we shall let our proposition as a p of n, where n is a positive integer. Then after that, we shall use the following two steps to prove that if the first steps are proved to be true, then it will be true, or it will hold true for all other natural numbers. Then after that, that will be our proof. Now the first step will be, we shall prove if Pn is true for the lowest possible values for positive integers. If this is true, then it is supposed to be true if we assume that a p of k is true, and then we shall establish a p of k plus 1. A p of k. So if it is true for p of k, then it must hold true that a p plus k also is supposed to be true. Now let's check some few examples. Now the question asks like that. You may be asked a question like that. Use mathematical induction to prove that for all positive integers n, we have that one. Final steps. That means let's have the question says you have to prove by mathematical induction. Then like that, this equals to what? N, as it is written there, n plus 1 over 2. But it can also be written like this and still remain to be the same. I do hope you understand that. Now, by the principle of mathematical induction, we have to prove some few first steps. Now, when n is equal to 1, that means we are trying to find the sum of this when n is equal to 1. That means actually we are talking about the first term. We're just trying to sum the first term. That means we shall have a 1 on the left-hand side, and then we shall have what in the next right-hand side. That means we have 1, then 1 plus 1 over 2. And then simplifying that, we shall have times what? 2 over 2. That means equals to 1. That means it holds true when n is equal to 1. Will it hold true when n is equal to 2? Let's check it out. Now when n is equal to 2, then that means we are trying to sum the first few two terms, the first two terms, the first one and the second one. That means if you try to look that much careful, we are trying to this way from r is equal to n of what? Of r equals to that thing there, as we discussed in series. That's what we are trying to. As we are doing the first one, that means r was 1 and n was 1. That means we had 1 on that hand side and 1 on that as 1 and 1 from the right hand side. That means we had that answer there. Now when n is equal to 2, that means we are trying to sum from r is equal to 1 to n is equal to 2. That means of what? Of r. We are trying to do to look for that. That means on this hand side we shall have a 1 plus 2, 1 and then 2, that's the last term, and then equals to what? This side it tells us that we have to put there 2 over 2 and then there 2 plus 1. And this side we shall have a 3, and that side, simplifying that, this and that is 1 and that is a 3, as it is seen there. That means for the first few terms it is true. Now let's go on with our proof. Now assume n is equal to k for all positive integers. Then what shall we have? In other books they say by hypothesis we have 1 by what is seen to k is equal to what? To k over 2, then k plus 1. Now we are trying to prove when n is equal to k plus 1. That means in the place of n there we shall add a k plus 1. That means what we are trying to prove is 1 plus 2 plus 3 plus down to k plus 1. That means the next term from there, there it will be equals to what? Our n now is k plus 1. That means is k plus 1 over 2. And then that side is what? Is k plus 1 plus 1. And this, remember, this is n and that is n. Remember that. So we have just plugged it there. Now simplifying that right hand side there, we shall have a k plus 1 over 2. And then what of that is k plus 2. Is k plus 2. So we are supposed to, from that sum, from this one, we are supposed to add another term there. And if our answer will be like that, that means we have proven that it holds true for all the positive integers n. Now, if we call this is equation 1, and this up to that point is equation 2, what can I say? Let's add a k plus 1 term. That means from there, let's add another term, a k plus 1, and we shall add that also on the right hand side. As you know in mathematics, if you add it there, then you are supposed to add on the other side of the equal signs. That means what shall we have? We shall have a 1 plus 2 plus 3 plus down to k, then plus k plus 1. We're adding a k plus 1, another term from the next term from that. That means also it will be like plus another term that we added it there. So it is k over 2, k plus 1 plus this term there. So k plus 1. So we are supposed to show this one resembles to that one. And if that is true, then it will hold true for all the positive integers. Now let's check it out. Now let's open the brackets there. We shall have a k square plus k, the whole over 2, plus k plus 1. And what is that? Then let's add those fractions. We shall have a k square plus k plus 2k plus 2 over 2. I do hope you understand how to add the fractions. Then let's factor out a half. And inside the brackets we remained with plus k plus 2k. You can simplify that to quadratic equation, and then find the factors of that. But I don't see the reason to go up to that point while we can have the factors from there. That means is over 2. Then factoring out k from these two terms, then we shall have a k plus 1 plus factoring out 2 from these two terms again, we have another k plus 1. Then finalizing that, we have a half times what? This and that one. We have a k plus 1 and k plus 2. Now you will see that this one is equal to something like that. That means it holds true for all the positive integers n. That means if you remember that much correct, we were not given a k in the equation. That means we have to conclude that for all positive integers, it holds true for 1 plus 2 plus 3 plus down to n is equal to n over 2, then n plus 1, because we have already tried to prove that there. So that is how we can prove by mathematical. Most of the students try to forget how to conclude the question. So you have to conclude your question. That you were supposed to prove that thing, and now you have come to that. You have arrived to that. And what makes you say this is through these steps. These steps have required you to say that this is true for all the positive integers. Now that is for the example number 1. What about the example number 2? Let's check it out. Now let's see example number 2. And what does it say? It says we are supposed to prove to what? To n of r square. And there we have n over 6, n plus 1. By using the principles of mathematical induction. It resembles the first one, but let's check it out. How can we prove this? Now, if you try to write this in series form, that means you have 1 square plus 2 square plus 3 square plus down to what? To n square, which equals to what? We know the formula is and the principles of mathematical induction tells us to prove this from the first few steps. That means we can prove for the first summation, the first one. That means we can prove this when r is equal to n is equal to 1. That means when n is equal to 1, it implies something like this. That is r square. So this equals to what? Equals to something like this. It's we are trying to look on for the first term. That is 1 square equals to, that side is n, and our n is 1 over 6. Then we have 1 plus 1, and then 2 times 1 plus 1. Now, in this left-hand side, we know it's 1. Now, let's simplify the right-hand side. We are supposed to get 1. And if it's not true for the first few steps, then we cannot continue on proving this, because it doesn't hold true for the first few steps. But if it's true, then we can be able to go on and prove. Then there is 2, and if you try to look that much carefully, there is 3, and then 2 times that is 6. Then we can have a 6 over 6, which equals 1. That means the left-hand side is equal to the right-hand side. Therefore, it is true for the first when n is equal to 1. Can we also, for fun, let's try when n is equal to 2. When n is equal to 2 r square. That means we are up to that point. So it is 1 square plus 2 square equals to what? When n is equal to 2, that means we are supposed to have a 2 over 6 there, and then we have a 2 plus 1, and then a 2. Then in this side, we know that there is 1 plus 4, that is 5, and then there is 1 over 6, and there is 3, and there is what? Is 4, and that is 5. Oh, that is 3, sorry, and that is 5. And then that and that, 3 and 3 goes, and then we are left with 5. That means it is true when n is equal to 1 and n is... Then we can go on proving the next few steps. Now, let's prove those next few steps. Now, let's assume it is true. It is true for what? When n is equal to k. And what is seen when n is equal to k? When n is equal to k, we have something like that. A 1 square plus 2 square plus a 3 square plus down to what? K square equals to what? K over 6, k plus 1, and then 2k plus 1. So that is, in other books, as I said earlier, they say it by hypothesis. And what we are required to do is, when n is equal to k plus 1. Now we add this term there. We add that term there. That means it will be what? 1 square, 2 square, plus a 3 square, plus down to what? To k square, then k plus 1. This, the whole square. That means we are supposed to have the following. Remember, our k now is k, our n there is k plus 1 from there. That means we have k plus 1 over 6. Again, there we have a k plus 1 plus 1. And again, there we have 2k plus 1 plus 1. Let's simplify that. This is what? K plus 1 over 6. Then k plus 2. And simplifying that is 2k plus 2 plus 1. That means is 2k. Oh, so that is what is required. That means the sum of that is equal to that. Now, calling this is equation number 1. And that is equation number 2. That is question number 2. What is the next step? Now, we were looking for the sum of the terms. And this was the sum when the terms ended up with a k. Now, what will be the sum if the last term will be a k plus 1? That means we shall have to add a k plus 1 on both sides of that. That means adding k plus 1 on both sides of equation 1. What shall we have? Up to that point, that means if we call that equation as that equation number 1 and number 2, then what follows? We have to add this on both sides. But remember, it is a k squared, or it is n squared. That means we shall have to add this one, but when it is squared to both sides of equation number 1. That means we shall have 1 square plus 2 square plus 3 square plus down to k square plus k plus 1 squared, as it is there. Then, and also on that side of that equation number 1. Equation number 1, that means is k over 6 k plus 1, 2k plus 1 plus k plus 1 squared. It is added on that side and also on that side. But if you try to look that much careful, you will see that a k plus 1 appears there and there. Then we can factor it out to simplify more the question. That is k plus 1. And inside the brackets, we shall remain with k. Remember, this is out of the brackets now. Then 2k plus 1 plus, but all of this is over 6, then plus k plus 1. Then what are we going to have? It is k plus 1. Then this, if we open the brackets there, we shall have a 2k square plus k plus 6k plus 6, and all of this is over 6. And if we factor out that 6 and inside the bracket, what are we going to have? We shall have a k plus 1 over 6, and that will be a 2k square plus 7k plus 6. Finding the factor of that quadratic equation, we find that the numbers to be added there will be there we must have 4 and 3, 3 and 4. That means what are we going to have? We're going to have let me finish up. And remember, what are we supposed to have now? We are supposed to get that thing there, because that is what is required. That is to say, we are going to have k plus 1 over 6, and there we have a 2k square plus what? Plus 4k plus 3k plus 6. And then what are we going to have? A k plus 1 over 6, and then we are going to have a 2k out there, and then we have a k plus 2. Then if we factor out a 3, then we are going to have a k plus 2. And what next from there is k plus 1 over 6, and there inside it is 2k plus 3, and also we have a k plus 2. And you will see that these results we have obtained there are the same as the results that are there when we were trying to look at it. Now remember, to conclude your question, as I did from the last example, then you conclude the same in this example, that this is true for all positive integers of positive integers, and as the procedures have shown, Now that is the second example. Can we check the next example and see how it goes? I do hope you understand what I'm... Now another kind of question we have been given there is, it says n cubed plus 2n is divisible by 3. Then we have to prove that is true for all the positive integers, n. Now how are we going to show that? So we have n cubed plus 2n, and this we are told it is divisible by 3. It is divisible by 3. Okay, let's check. We know that we have to show the first few steps, the first, the second, and then some few first steps, and then if they are true, then we are allowed to go on and prove the proposition by the principle of mathematical induction. Now let's say n is equal to 1. When n is equal to 1, this will imply that n there will be 1 raised to 3, and then we have a 2 times 1, and then it implies that we have a 1 plus 2, that is 3. Oh, is 3 divisible by 3? We know it is divisible by 3. That means when n is equal to 1, it holds true. Now when n is equal to 2, will it hold true? Now let's check. So we have a 2 raised to 3 plus 2, and then there we have a 2. And then there we have 8 plus 4 is equal to 12. Is 12 divisible by 3? Yes, it is divisible by 3. That means, okay, these first few steps have shown to be true. Now we can go on proving this by the principles of mathematical induction. Now assume n is equal to k. That means we can have a k raised to 3 plus 2k, and this is supposed to be divisible by 3. That means is certain kind a multiple of 3. Now, what are we required to prove? When n is equal to k plus 1, will it hold true? Will it still be true that this factor, once we plug it there, will it also be divisible by 3? Now, let's check it out. Let's check it out. Let's check it out. How will it be? So, it will be a k plus 1 raised to 3 plus 2 k plus 1. Is it divisible by 3? That's what we are trying to say. That's what we are trying to look. Now, let's see. So, if we try to open the brackets there, you can use Pascal's triangle, and then what shall we have there? Shall have a k raised to 3 plus 3k plus 3 there, k squared, then k plus 1. Again, plus what? A 2k plus 2. So, simplifying that left-hand side there. Now we are trying to say, to check whether this is also divisible by 3. Is also divisible by 3. Now let's check it out. So, if you try to see how it holds, we can collect this one and that one. Shall we? Okay. And then do we have like terms? Okay, we have a constant there, and also we have a constant there. So we have a k raised to 3 plus 3k square plus 3k plus, okay, we have 3k there, and then we have a 2k again. Why have I left that like that? We shall see in the next step. Then this and that is 3. But remember, in the last steps, we have been proving this is true. We have been proving this is true. Can we find that those factors there? You will see that they appear there, somewhere there. So we have a k raised to 3 plus 2k somewhere there, okay? 2k there. And also we are left with what? Let's see. We have a 3k square plus a 3k plus a 3. Then what are we going to have? We have a k raised to 3 plus 2k plus, can we factor out 3 there? Then we can have k square plus k plus 1. But remember, this one is also divisible by 3, as we have been shown there. So that is 3m plus k plus 1. Then we can also factor out 3 there again. Then we shall have m, then we have a k square plus k. So the whole of this is, since it is multiplied by 3, that means it is divisible by 3. The whole factor is divisible by 3. That means by the principles of mathematical induction, we have shown that n raised to 3 plus 2n is divisible by, for all positive integers n. For all positive integers n. For all positive integers n. I do hope you understand. That question was very simple, and it's a good reminder for you to understand and to try to find some more questions on such kind of questions and try to solve them. Now let's check the last example, the fourth example for today. That is, we are supposed to prove by the principle of mathematical induction that r cos t plus I sine t, and all of this is raised to n, is equal to what? Is equal to r raised to n, and all of that is cos nt plus I sine n t. So we are supposed to prove that by the principles of mathematical induction. It's so simple. It's so simple. Now we know that the first step, the first few steps is to prove for n when n is equal to 1. Now, when n is equal to 1, that is to say, we have from the left hand side we have r cos t plus I sine t, and all of that is raised to 1 is equal to what? To r raised to 1 of what? Cos our n there is 1, that means it will still be t plus I sine t. That means for the first one, we can simplify that by, it's so simple. Okay, this equals what? To r cos t plus I sine t. So the first one holds true. First one holds true. Now when n is equal to 2, will it hold true? And then we shall prove when n is equal to k plus 1. Now let's check when n is equal to 2. Let's see. So r cos t plus I sine t raised to what? And this is raised to 2 is equal to r. We have our n in there, which is 2. Then we have cos of 2t plus I sine 2t. So it holds true. Okay, now let's see how can we prove when n is equal to k plus 1. Now let's assume. Now these steps can allow us to assume that when n is equal to k, then this is true. R cos t plus I sine t, and all of this is raised to k is equal to what? Is equal to r raised to k of what? Cos kt sine kt. And what are we required to prove when n is equal to k plus 1? That means we are going to have the following. We are going to have r is equal to r cos t sine t raised to k plus 1. It is supposed to be like this. R k plus 1. Then we have a cos k plus 1, and that is in brackets by t. Then I sine k plus 1, and that is in brackets by t. So that is what we are required to show. That's what we are required to show. If all these are true, if these are true for all the positive integers, then this also should be true. And how do we do that? Now, calling this is equation number 1, and this is equation number 2 that is supposed to be proved. Then let's do the following. Now let's multiply. Let's multiply by r cos t plus I sine t on both sides of equation number 1. That means we go back there to equation number 1 and we multiply by this factor on both sides of that. Now let's be that much careful there. That means we have r, then in brackets we have cos t plus I sine t, then is multiplied by that on both sides, that is r, and remember there is k, that is there is k, is multiplied on both sides by that. That is, we are going also to have r cos t plus I sine t on the left hand side, and on the right hand side what are we going to have? So we are going to multiply also by that factor there. So we are going to have, let me write there for the space there. Now this side is also multiplied by that. So we have r raised to k of what? Of cos kt plus I sine kt, and all of these is multiplied by that factor there, r cos t plus I sine t. Now let's be careful there in opening those brackets, in opening those brackets, in opening those brackets. Now let's see, what are we going to have? What are we going to have? Now in this side, remember this, there is 1 there and there is 1 there. Now in exponents we did this, in indices that will be r, that is k is there, then it will be k plus 1. That means a k, if you open the brackets, the k will come there, and then plus 1. Then we shall have the following, cos t plus I sine t, and also that is k plus 1. Or you can just write that as r cos t plus I sine t, then all of these is k plus 1, is k plus 1. Now let's open the brackets, let's open the brackets, let's open the brackets, and this and that, r raised to k and r raised to 1 will be r raised to k times r. Now let's open this part and that part. That is, let's say we have a cos times that cos. That means we have cos kt times cos t. Then cos times that sign, that means we have plus I cos kt sine t, plus, let's have this and that. That means we have I sine kt cos t, plus I and I, it is I square. Then sine, we have sine kt sine t, and all of this is in brackets. Now can we collect like terms? Can we collect like terms? But remember, I square is equal to -1 from complex numbers. That means instead of writing there I square, we shall write a -1. And collecting like terms there, we shall collect the ones which are real. That means having a -1 there, minus sine kt sine t, that makes that number to be real, not complex again. That means we shall collect that one and that one. That means we shall have r k, or r, then this and that one is equal to cos kt cos t minus sine kt sine t. Now that is for real, and for the complex side, that means we have I this one and that one. We have cos that one, cos kt sin t, plus this one, that is sin kt cos t. Cos t. Now from the double angle formula, we know that when you have cos of A plus B, and when you have sine sine of A plus B, what are the answers? Cos of A minus B and cos sine of A minus B. And if you try to look that much careful, you will find that this thing here, this equals to a cos of what? Of kt plus t. And if you try to look that much careful to that thing there, you'll find it is a sine of what? Kt plus t. Now let's simplify that so that it can look much more simple. That is r, and remember there we have 1, that is k plus 1. And in brackets we have now cos kt plus t plus I sine kt plus t. Let's simplify that much more. Again we have r k raised to k plus 1, and there we have cos, factoring out the t, there shall have a k plus 1 t plus I sine k plus 1 t. And you will see that these results we have obtained there are equal to the results from that thing there. Then you can conclude that by the principles of mathematical induction, this holds true, that this holds true, this holds true. And that's how we try to prove the question of that form. The question of that form. It's so simple. Most of the students, when sees things like this, they start vibrating, and some sweat coming out of the palms of the hands, and then they fail to attempt the question. But it's so easy. Just follow the steps and the rules, and then I assure you, you must arrive to the conclusion and to the answer that you are supposed to get. Now, from those few examples, I hope you have reminded yourself much better on principles of mathematical induction, and from there I will leave some few questions for you to handle, for you to perform. Just follow the steps, and you will arrive to the last answer. But remember to conclude. Most of the students do forget to conclude. The conclusion is there. You have the conclusion already. So just say from all the by those proof you have been proving, then this is true for all the positive integers n, for all positive integers n. Now let's see the exercise. Now, as I have said, I will leave you some few questions for you to handle, and they are very easy for you to perform. As the first question is there, and the divisibility, as we did from the, I think is the third example, if not the fourth, the third, and we have the next one. They are very easy examples to perform. So please try to check on those and find more questions. Find more questions from the books, from the past exams, and try to handle those. And I assure you, you will understand that much better the principles of mathematical induction. The principles of mathematical induction. Please, please, follow the steps. Follow the steps. The steps are very few and they're very easy to follow. Just follow them, and then you will be there. Let me leave you there for today, and I hope you enjoyed the lesson. And just stay at home, stay safe. And while you are there at home, remember to solve different kind of questions. on mathematical induction, on series, on quadratic equations, whatever that are there, but mathematical questions, just solve them. And I assure you, you'll be good in mathematics. Thank you. All the best.